Hello and welcome to Electromagnetics 1. Dr. Trample here. This is lecture 19A. Today we're going to be talking about wave polarization. Well, what exactly is polarization? Polarization is the locus or the location of the tip of the electric field at a given point as a function of time. Typically, the electric field is in a plane perpendicular to the direction of propagation. There are three kinds of polarization: linear, circular, and elliptical. For linear polarization, the tip of the electric field describes a straight line, as shown here in figure 1. What you're seeing in this part of the figure right here is an electromagnetic wave that's propagating in the plus z direction. So it's propagating in the positive z direction. And you're seeing the wave essentially as a function of space at a particular time. So time has been frozen, and we're just looking at what the wave looks like as a function of time. The tip of the electric field is going to move along this blue line as time progresses. So at omega t equals 0, it points down and to the right here, and then as time increases, this vector will shrink, and then it'll actually start to point in the opposite direction until omega t equals pi, and then it'll shrink back down again and point in this direction, and so forth, sinusoidally. The tip of the electric field moves along a straight line. That's how you know that it's linear polarization. Now, for a uniform plane wave, we know a uniform plane wave is linearly polarized if it has only one component, or when its transverse components are in phase. Let's explore that quantitatively here for a moment. For a wave that travels in the plus z direction, we can write down the x component of the electric field, Ex, in this way. It's equal to some magnitude times cosine of omega t minus beta z plus some phase. Okay, phi sub x is the phase of the x component of the electric field in this case. Similarly, we can write down an expression for the y component of the electric field, some different constant, times again cosine of omega t minus beta z plus the phase of the y component. Here beta is called the wave number, and omega is the frequency of the wave in radians per second. Okay. The composite wave, then, we can essentially write this thing down as a vector. We can write the electric field as a vector in this way, just placing the x component here in front of x hat and the y component in front of y hat. Now we know that this wave is going to be linearly polarized when the phase difference, which is just simply the phase of the y component minus the phase of the x component, is equal to some integer times pi. All right, that's the phase condition that we need for linear polarization. Well, why does this particular phase condition lead to linear polarization? It turns out that if the phase difference is some integer multiple of pi, then the two components, the x component and the y component, will have the same ratio at all times. Let's see if we can demonstrate that. First, let's say, for example, that the delta phi is equal to 0, or there's no phase difference, which is to say that the phase of the y component is the same as the phase of the x component. We'll just simply call that phase phi. And we're going to pick a particular position, in this case z equals 0, and let time run. Then the ratio of the x component to the y component is given by this expression, and you can see that so long as the phases are the same, the cosine terms cancel out, and for all time, the ratio of the x component to the y component is just the ratio of the amplitudes. That's what you need if you want to relate this to the equation for a line. that's the same condition that we have for the equation of a straight line, which is to say that the ratio of x to y or y to x is equal to some constant. So it's the exact same thing as the condition to have a straight line. Now, linearly polarized waves may be generated or created by a couple of different kinds of antennas or sources. You can use a dipole antenna, or you can use a laser. Those will also create linearly polarized waves. Now, circular polarization occurs when the x and y components have the same magnitude, so those constants are the same, and the phase difference between them is an odd multiple of pi over 2. We express that in this way. We say delta phi is equal to the phase of y minus the phase of x is equal to plus or minus 1/2 plus 2n times n pi, where again n is an integer. So let's look at, in order to explore circular polarization here a little bit, let's look at the situation where the phase of the x component is 0 and the phase of the y component is equal to minus pi over 2. Substituting that into the expressions for the x and y components that we had earlier, we have this expression here for the x component, E naught cosine omega t minus beta z, and then this expression for the y component, E naught cosine omega t minus beta z, plus the phase here, which is equal to minus pi over 2. Okay, so in order to see what happens to the polarization of the wave over time, we're going to look at, we're going to refer to this figure right here. This is figure number 2. Okay, let's go back up here for just a second. So again, we're going to fix a particular position, in this case z equals 0. All right, when omega t is equal to 0, then the electric field is going to point in the plus x direction. Why? Well, if z equals 0, these terms fall out here, and then if omega t is equal to 0, we have cosine of 0 here, that's 1. And if omega t is equal to 0 here, we have cosine of minus pi over 2, which is equal to 0 for the y component. So the x component is 1, the y component is 0, when omega t is equal to 0. When omega t is equal to pi over 2, so we're letting time run a little bit now. Now we have, and for the x component, we have cosine of pi over 2, that is 0. And for the y component, we have the cosine of pi, cosine of 0, which will be 1. So in this case, when omega t is pi over 2, the electric field points along the plus y direction. Let's go down to the figure now. Okay, so here we are at omega t equals 0. We decided that the electric field points entirely along the x direction, and then at omega t equals pi over 2, we decided it points entirely along the y direction, and it can be shown that at omega t equals pi, it points along the negative x direction. At omega t equals 3 pi over 2, it points along the negative y direction. And then at omega t equals 2 pi, it'll point along x, and so forth, rotating around in a counterclockwise direction. That is an example of left-handed circular polarization. Let's go back up to our expressions here for a moment. Excuse me, that's an example of right-handed circular polarization. Why? This is an example of right-handed circular polarization because if you put your thumb in the direction of propagation, which is the plus z direction, your fingers will curl around in the direction that the electric field is moving over time, in this case the counterclockwise direction. So this is right-handed circular polarization. Let's look at an example of left-handed circular polarization. All right, you can generate a left-handed circular polarized wave if you again allow the phase of the x component to be 0, but in this case we're going to allow the phase of the y component to be positive pi over 2. Okay. Again, let's fix a particular position, z equals 0, and we're going to let omega t be equal to 0 initially. In this case, it's the electric field will be pointed along the plus z direction. When omega t is equal to pi over 2, the electric field is going to point in the minus y direction in this case. Let's go back to our figure. Okay, so when omega t equals 0, again, you start totally polarized along the x-axis, but in this case, when you have the phase of the y component equal to pi over 2 instead of minus pi over 2, then when omega t is equal to pi over 2, you're polarized down here in the minus y direction. At omega t equals pi, you'll be pointed in the minus x direction. At omega t equals 3 pi over 2, you'll be pointed in the positive y direction, and so on and so forth, rotating around in a clockwise fashion. This is called left-handed circular polarization because if you take the thumb of your left hand and point it in the direction of propagation, your fingers curl around in the direction that the electric field processes in as time increases. So we've dealt with right-handed circular polarization and left-handed circular polarization, and we've shown why they're called left and right-handed. But how do we know that, in fact, the tip of this electric field as it moves around in time describes a circle? Let's look at the components of the electric field again at z equals 0 when the phase of the electric field is equal to 0 and the phase of the x component is equal to 0 and the phase of the y component is equal to pi over 2. Okay, in that case, again, we have this expression for the x component of the electric field and then this expression for the y component of the electric field. And it turns out that cosine of omega t plus pi over 2 is equal to sine of omega t. All right. So the y component is equal to minus the amplitude times sine of omega t. So therefore, if we square the x component and we square the y component and we add them, we get this expression. Cosine squared plus sine squared is simply equal to 1. So it turns out that ex squared plus ey squared is equal to e0 squared. This is the equation. You'll recognize this as an equation for the circle. So we know that no matter what time we are at, the magnitude of the electric field is going to stay the same, and it's just going to move around in a circular pattern. Elliptical polarization from a mathematical perspective is almost identical to circular polarization. Elliptical polarization occurs under the same phase conditions as circular polarization. However, for elliptical polarization, the amplitude of the x component is different from the amplitude of the y component. That just will get you the equation for an ellipse instead of the equation for a circle. Okay? I think that finishes off this little lecture. Hope it was helpful to you, and we'll see you in lecture number 20.